So for today's talk, I've decided to talk a little bit about what I did in my PhD studies. And while now I am a postdoctoral researcher at COTIO, the talk I'm going to give today, which is entitled Collective Decision Making on Networked Systems in Presence of Antagonistic Interactions, is part of a project that I did in collaboration with my previous supervisor, Professor Altafini. But let's start. So, sorry, there. This is the outline of my talk. I will start by giving some background, some motivation, and the problem statement that we looked at. And then the talk will be divided in two parts. The first part, I will introduce the model for a collective decision making over sign networks and introduce notions of over sign networks. And then the second part will be dedicated to an application or a concrete example of the previous work. So the problem that we want to address is that of a group of agents exchanging opinions with the objective of reaching a decision. And as you might know, in nature it's possible to find several examples of collective decision making in animal groups, so collective behavior in animal groups. For instance, we have the selection of a new hive in a colony of honeybees, or the selection of the departing time in a flock of birds. And the common factor between these two examples is that a decision is reached through the collaboration between the agents. However, this assumption might be not very realistic in considering different scenarios or applications that we're interested about, such as social networks or parliamentary systems. And here is more plausible to assume that both cooperative and antagonistic interactions coexist between the agents. So for this reason, the problem that we are interested in studying is collective decision-making in presence of antagonism. And to solve this problem, we need two ingredients. We need a network or a sign network, so a framework that is able to capture these cooperative or antagonistic interactions between the agents, where the idea is that a positive weight in the network, on an edge in the network, represents a cooperative interaction, while a negative weight represents an antagonistic interaction. And then we need a model which describes the evolution of the opinions of the agents in time. Was equilibrium points represents the possible decision for the collective decision-making process. Regarding the choice of model, we have been inspired by previous works in the literature, and while I will introduce a detailed analysis later on in my talk, I just want to quickly recap the features of this model. So when we look at this model, we can see that it's made of two parts, a diagonal and an off-diagonal part. And the diagonal part is described by a matrix delta, which represents the inertia of the agents to the development of an opinion. So basically, it's the term that drives the opinions of the agents to zero. And then we have an off-diagonal part, where we have, which basically describes the interactions between the agents. We have the identity matrix A, which determines in who communicates with who. And a nonlinear, and the idea is that each agent I transmits its opinion to its neighbors of the network through a nonlinear function psi I, which we assume being sigmoidal and saturated with the idea that extreme opinions are moderated. And then finally, the interactions between the agents are modulated by a scalar parameter pi. In this model, the equilibria, as I said before, represents the decisions for the community. And the scalar parameter pi is what we call the social effort or the strength of the commitment among the agents. Then under a Laplacian assumption on the matrix delta, meaning that this matrix delta is the weighted degree matrix of the network, then tools from bifurcation theory has been used to show that this model exhibits a pitchfork bifurcation behavior, meaning that from a neutral state or deadlock state of no decision, then by increasing the social effort and hence reaching what is called the right amount of commitment, two alternative decisions can be achieved. So again, I will give a detailed analysis later on. I just would like you to remember this pitchfork bifurcation figure or feature of the model. What we want to do I wanted to do in my work was to adapt this model in order to take into account the fact that both cooperative and antagonistic interactions might coexist between the agents. So then we want to look at this model over sign networks. So this means that first we need to introduce some notions of regarding sign networks. And then a natural way to start is by introducing the notion of a sign Laplacian of a network. So in the literature of sign networks, it's possible to find different definitions of sign Laplacians, but the one that we have adopted is the following one. And at a glance, it might seem very similar to the standard notion of Laplacian. But the difference is in how the weighted degree matrix of the network is defined, so the matrix delta. And as you can see here, each element I of the matrix delta is given by the sum of the elements in the ith row, taking an absolute value of the matrix A, meaning that all the elements in the matrix delta are strictly positive. And in this talk, I will more focus on the normalized sign Laplacian of the network. So the scaled version, so basically the Laplacian obtained by having the identity matrix on the diagonal. And then a feature of this normalized sign Laplacian is that by defining the matrix delta in such a way, we obtain that all the eigenvalues of the normalized sign Laplacian are non-negative, which is as in the standard Laplacian case. Now, the second notion that I want to introduce of sign networks is that of structural balance. And we say that a sign network is structurally balanced if the group of agents can be divided into two groups of mutual friends linked only by hostile relationships. And it is structurally unbalanced otherwise. So what does it mean this in the social context? So basically the difference between a structurally balanced and a structurally unbalanced network in the social context basically a structurally balanced network represents situations where there is less social tension between the agents. So for instance, if we consider parliamentary systems where the parties have to negotiate, they have to discuss, they have to talk to each other before taking any action or any decision or any vote, then a two-party parliament represents a structurally balanced network, a situation with less social tension, while a multi-party parliament represents instead a structurally unbalanced network, so a situation where there is more social tension between in the network or between the political parties. And analytically, it's possible to give two equivalent conditions for structural balance. Oh, I'm sorry. I will first read them and then explain them. So we say that a network is structurally balanced if and only if there exists a signature matrix, so that by applying special transformations, which are called the signature similarity transformations in the graph theory literature, then we obtain a graph with positive edges. So the idea is that these transformations consist of changing the signs of all the edges adjacent to a set of nodes. Let's look at this example. For instance, in this case, if we change the sign of all the edges adjacent to node 4 and node 5, what we obtain is a graph with only positive edges. And the second condition, or the second equivalent condition that I focus mostly on, is that a graph or a network is structurally balanced if and only if the smallest eigenvalue of the normalized sign Laplacian is equal to 0. Which also means, as a consequence, that the graph is structurally balanced if only if, unbalanced, sorry, if only if the smallest eigenvalue of the normalized sign Laplacian is strictly greater than 0. But then if we consider a structurally unbalanced network, it is natural to ask how far this network is from a structurally balanced state. So basically the level of imbalance of a network. And the standard measure in the literature is the frustration index, which I will just call frustration in the rest of this talk. So the frustration index is defined as the minimum of all possible signature similarity transformations. So this transformation that I've introduced before of a certain energy functional, which depends on the normalized sign Laplacian of the network. And now we don't have to focus on the formulation that might seem confusing, but what is relevant is that the computation of the frustration of a network is an NPR problem, which means that this basically the idea is that it's difficult to compute for highly connected or big networks. So luckily, there is in the literature, there is another measure to measure the graph distance from a structurally balanced state, which is the algebraic conflict, which is simply defined as the smallest eigenvalue of the normalized sign Laplacian. And by computing and compare the frustration and the algebraic conflict for different networks, one can actually observe that the smallest eigenvalue of the normalized sign Laplacian is actually approximates well the frustration of the network. So now I have introduced basically all the notions that we're going to need for sign networks, and the intuition or the notions that I would like you to remember is that there is this notion of frustration of a sign network, which represents the amount of social tension in a network, and that this frustration can be well approximated by the smallest eigenvalue of the normalized sign Laplacian. Now, if we go back if we resume our model for collective decision making over sign networks, we can notice that the only difference with respect to the model that I've introduced at the beginning of my talk is that now we need to consider sign networks, which means that if we look at the elements of the adjacency matrix A, then we have that the sign of each element represents the type of interactions between two agents. We could be friendly or unfriendly. And then the absolute value of these elements represents the amount of trust or distrust between two different agents. So as before, we have a Laplacian assumption on the matrix delta. And it is actually useful to rewrite the system in the following forms, which highlights the normalized adjacency matrix of a network, which is noted by the letter H. And the reason is that then it's easier to see the relationship with the normalized sign Laplacian of the network. And just a small parenthesis is that by doing so, we can also, the advantage is that we can actually express monotonicity or distance to monotonicity of this nonlinear system in terms of structural balance of the sign network, which is actually, yes, a static property of the network. So what we want to do then is not only study how the social effort parameter, which we denoted by pi, affects the behavior of the system in terms of existence and stability of its equilibrium points, but also how the presence of antagonism in the network between the agents affects the behavior of our system. Antagonism that we represent using this notion of frustration of sign networks. So I will now show the results that we have obtained for structurally balanced and structurally unbalanced networks I will first introduce the analytical results and then give an interpretation in the social context. So, okay, let's start with the structurally balanced case. And what we did was a bifurcation analysis. So if we look at the figure on the right, this is a bifurcation diagram. So it depicts the equilibrium points of the system as we vary the social effort parameter pi, which in the analysis plays the role of a bifurcation parameter. So if we look at the system, what happens is that when pi is less than 1, the origin, here depicted with this black branch, is the only equilibrium point in the system, and it is globally asymptotically stable. Then, when pi is equal to 1, the system undergoes a pitchfork bifurcation, meaning that the origin becomes a saddle point, and new equilibria, here depicted with these red branches, appear for the system, which will be locally asymptotically stable. And then further increasing the bifurcation parameter pi, the system undergoes a second pitchfork bifurcation, and the new equilibria, here depicted with these blue branches, appear for the system. And through numerical simulations, we can observe that this equilibria might be stable or unstable. Sorry, I just need a bit of water. Then what we did was also to look at the structurally unbalanced case. And what we actually observe, interestingly, is by redefining the threshold bifurcation values for the social effort parameter, we observed that actually the behavior of the system was the same. So we had the origin as the only equilibrium point, and then we had two pitchfork bifurcations at the values pi1 and at the value pi2. So before going into the interpretation of the results in a social context, I just would like to give you an idea on how the proof of the first bifurcation for the structurally unbalanced case had to be made. And the reason is that in this case, the system is not monotone. And therefore, the technical tools that one has to use to carry the proofs might differ from previous works in the literature. So, for instance, if we want to prove that the origin is a globally asymptotically stable equilibrium point, we had to define a Lyapunov function and then show that this Lyapunov function was strictly less than 0 for all the domain except the origin, while regarding the proof of existence of a pitchfork bifurcation, the idea, what we did was to use a procedure called Lyapunov-Smith reduction, which maps the system into the center manifold and then show that its partial derivatives follow the following conditions, which actually denote a pitchfork bifurcation at phi1. So I don't really want to talk more about the proofs, and I can answer questions if you're interested, but what I just wanted to say is that when also to prove other results, such as, for example, stability of equilibria, the proofs and the technical tools that we had to use differ from previous works in the literature due to the presence of antagonism in the network. But now let's continue. So I will not introduce any more proofs. And now that we actually shown that there is this existence of two pitchfork bifurcations at these values pi1 and pi2, which is also illustrated in these figures, which represent the smallest two eigenvalues of the normalized Jacobian at the origin. Now it's time to give an interpretation in terms of in the social context of our results. So what we have shown is that when the social effort among the agents is small, then no decision is possible for the community will end up in a deadlock situation. But then when the agents have the right amount of commitment, then two decisions will be possible for the community. And however, when the social effort or the commitment increase even further, the community ends up in a situation of overcommitment, where several decisions might be possible. Now that we have understood how the system behaves as we vary the social effort parameter, it is also interesting to understand how, how the presence of antagonism influences the behavior of the system. And to do so, we need to basically focus on the relationship between the threshold values pi1 and pi2 for the social effort parameter and the frustration of the network. So we can observe that these threshold values depend on the two smallest eigenvalues of the normalized and Laplacian. And we have that the smallest, the first threshold value, we can notice that it is equal to 1 and it is fixed for structurally balanced networks. But then since it depends on the smallest eigenvalue of the normalized and Laplacian, we know that basically then it will depend on the frustration of the network for when the network is structurally unbalanced. While the second threshold value pi2, well, it depends on topological properties of the network, such as algebraic connectivity in the structurally balanced case. But the most important thing, it is actually independent from the frustration in the structurally unbalanced case, meaning that the gap between pi2 and pi1 will decrease or will shrink as the frustration will increase. So to summarize what we have seen so far, we have shown that we have made the following observation and show that the first threshold value or the threshold value for the first bifurcation grows with the frustration of the network, meaning that the higher is the frustration, the higher is the social effort that is needed to achieve a decision. And also the smaller is the interval for which only two alternative decisions exist for the community. So now I would like to conclude the talk with a concrete application of this work and of these results, which is political decision making. And we decided to look at the government formation process in countries with a parliamentary system. And this process starts with a legislative election, after which each political party gains a certain number of seats, depending on the amount of votes that it receives at the election. And if basically no party or coalition had managed to secure a majority in the parliament, then a negotiation process will start between the political parties. And the outcome of this process will be a vote of confidence to a candidate cabinet coalition. And this government formation process might be lengthy or a complex and long process. And for instance, in the past 10 years, we have seen an increase in the duration of the government negotiation talks, here defined as the number of days between the election day and the day the cabinet is sworn in. And this increase in the duration of the government negotiations has happened not only in countries which are actually famous for this type of behavior, such as Belgium, but also in Germany and in Sweden. Actually, inspired by the Swedish election of 2018, we wonder if we can actually use our model and our intuition or the dynamics to explain this behavior. So the idea is that we would like to model if we look at the government formation process as a collective decision-making system in which the parliamentary members are the agents, which need to cast a vote of confidence, so a decision to the candidate cabinet coalition, and in where we can think that the social effort that the parliamentary members have to have corresponds to the duration of the government negotiation phase, then using the intuition from our results in the dynamics, then if we map the parliament into a sign network and we measure its frustration, then the idea is that the duration of these government negotiations should correlate well with the frustration, meaning that the higher the frustration, so the higher the social tension, the longer is the government formation process expected to be. Higher frustration, longer period of negotiations. Sorry, a little bit of water. And to evaluate these hypotheses, we have analyzed the legislative elections in 29 European countries in roughly the last 40 years. And what we did was to actually calculate the Pearson's correlation index between the frustration of these parliamentary networks and the duration of the negotiations, the cabinet negotiations. And this procedure is here illustrated for the German elections. So we have collected data on the amount of days and on the frustration, and then calculated the Pearson's correlation index. So the first step is then to construct a parliamentary network. And a parliamentary network is, we define it as a complete undirected sign graph in which each parliamentary member is a node. And using under the assumption that we have that parties behave as homogeneous entities, we then could group parliamentary members into a big party node. And then we made the assumption that while we have collaboration between parliamentary members which belong to the same party, we had rivalry between parliamentary members that belong to different parties, obtaining all against all sign parliamentary network, which also meant that the adiasis matrix of the network was a block matrix. Then, after constructing these parliamentary networks, we wonder if these parliamentary networks were actually structurally balanced or unbalanced. Remembering that a structurally balanced network, parliamentary network, is a network, basically is an example of structurally balanced parliamentary network is the one on the left. So, for instance, when we look at in this example, we can see that the frustration of the parliamentary networks, in this case for the Italian country, we can see that the frustration here depicted with this blue dot is always greater than 0, meaning that the corresponding parliamentary network are not structurally balanced. And if we look at, and in this picture, we actually show or illustrate the frustration for all elections in all the countries that we have taken into account. And we can see that the frustration, no matter the election, is always greater than 0, which means that in general, the parliamentary networks are structurally unbalanced. So these are the results that we obtain. So in terms of average correlation between the duration of the government negotiations and the frustration of the parliamentary networks for each country, for each of the 29th country. And we obtain a value of correlation of 0.42, which is actually quite good considering how simple is the model that we are looking at. And I have not put slides about this, but actually for countries where we have a negative correlation, that is actually such as Czech Republic, Estonia, or Greece, there is actually an explanation why the correlation is so low. And then we decided to extend this analysis to take into account a bit more complex scenarios when constructing the parliamentary network. So we thought it was more realistic to actually include also ideological differences between the political parties. So while before the IDSSE matrix was unweighted matrix, now we have the weights that represents how ideologically distant two political parties are. And to select these weights, we looked at two different scenarios, which are called relay and optimized. The first one, where basically we looked at the electoral manifestos. So we looked at basically the left-right positions of the party given their electoral manifestos. And then the second one, while having optimized and randomized left-right political grid. And the interesting thing is that, let me just pick again the Italian elections, is that while, for example, this correlation between the duration of the government negotiations and the frustration in the first scenarios that we looked at, the all against all scenario, was quite low for the Italian elections, then we noticed that by adding these ideological differences between the parties, then we obtained that correlations actually went up to 0.45 and then 0.95. And the reason is that you can think that in the Italian elections, the network, in the Italian elections, they are quite fragmented, and there are many. It's a true multi-party system. So it was interesting to see this increasing correlation between the government negotiations and the frustration. And in the second figure, I plotted the results that we obtained in the average correlation for all the countries and for all the scenarios. So from 0.42 to a correlation of 0.69 over all countries. So to conclude, what I did, an overview of what I did in my PhD studies was to study decision-making processes in community of agents where both cooperative and antagonistic interactions coexisted. So where we had agents that were both friendly or rivals between each other. And then we wanted to study the qualitative behavior of these processes or these systems, as not only as we vary the social effort or the commitment between the agents. And what we observed was a pitchfork bifurcation behavior where a deadlock is broken only if the agents achieve the right commitment in each other. But also we studied how the frustration, so the amount of disorder or the amount of social tension in the sign networks affected the behavior of the model. And what we have shown is that the frustration influenced the level of commitment that is required from the agents in order to break the deadlock and reach a decision. Finally, we look at an application of these results. And in particular, we decided to model the government formation process as a collective decision-making process. And using the intuition from our previous results, we showed that, and also collecting data in 29 European countries, we show that the frustration actually correlates well with the duration of the government negotiation phase. So this was my talk, and thank you for listening and for again inviting me to give a talk at Digital Futures.